When we start dealing with exponential growth and decay, you got to be able to tell whether it's exponential growth or not. Okay, most of the time these are going to come in the form of a word problem, and a lot of times if it's a comparing problem, they'll give us a linear growth, a constant growth, and an exponential growth, and ask us to compare stuff about them. We've got to be able to differentiate between the two. So we can tell a problem is growth or decay because the problem has a stated change and a percentage. Exponential growth and decay, the change is stated as a percentage as we work through, instead of a constant value, meaning your job gives you a 2.5% increase each year. That's exponential because my change is stated as a percentage of what I'm currently making. If your job gives you a $500 increase each year, that $500 is how you're changing, and it never changes itself. So that's going to be constant or linear growth. Now, when you learn this in the very beginning, the formula you learn to find your balance of these things look like this. It was an initial times 1 plus a rate to the power of t, where t stood for time. Rate. Where does the rate come from? Well, if we look, this is our exponential, right? We know our initial, let's use this example up here, is 35%. So the initial is always going to be what you're starting with. The time, you got to look at here, this is intervals and how the percent is applied. The rate is the percentage. So your rate here, if we use this example, would be 2.5%. And it's each year, so that means we'd be measuring t in years for this setup, okay? And you can see, in general, since these are exponential, this follows our exponential family parent function that we listed. A was our transformation there. We had a B that was our base with our power being X. This just puts words in place of those variables so we understand which spot to put stuff. So if I were to set this up using this first example, and I wanted to figure out my balance. Now my balance is a very generalized word. Balance could be however much you have after in a year. Okay, this time we're measuring salary because we're going to do this one. So our balance is going to be our initial, which was $35,000. And we're going to do our parentheses. The 1 doesn't change. The t stays in there because what it is I'm getting a formula that will allow me to plug in t's and find out how much money I'd make at the end of that time frame. Now the rate is what we need to be careful with. The rate that we were given was 2.5%. Now this says this is a percentage in decimal form. Anytime we do math with a percentage, we need to take this decimal point and move it 2 places to the left. So this percentage in decimal form is 0.025. Whenever you do these percentages into decimal form, no rounding, write the whole thing in there. So this is going to be plus 0.025. You probably wouldn't leave the plus in there, meaning that you would write your equation 35,000 1.025 to the t. And what this equation allows us to do, I'm going to erase where I found the rate. The reason you write this equation, and we're going to use this with the other forms too, so we'll kind of practice it. At this point, you would be asked, what's my salary after 5 years? Well, if we wanted our salary after 5 years, our t would become 5. So we would figure out, we'd go 35,000, 1.025 to the power of 5. And we would plug that in. So let's bring up the Desmos Scientific Calculator and see what we get. And if you hadn't used this one is really nice, especially on the computer. So we had 35,000, 1.025 to the power of 5. And our answers over here, we got 39,599. And now this is money, so we're gonna round it to 2 places, 29. So this is what we get exactly. From the calculator. But if you were to write your answer out, put your information back in, $39,599.29 per year. That's the extent of what we can do with this exponential, and this is what we had done with it before. Now, this is not the only way that interest can be calculated. In fact, this is not the normal way that you'd end up dealing with this. If we dealt with a credit card, the credit card deals with monthly interest, right? They don't charge you everything at the end of the year and make you make a payment. They make you make a payment every month. But what you have to be cautious with is that they tell you a percentage per year, and then what they do is they break that percentage down and charge you a portion of it each month. It's kind of weird. But we end up with compound growth and decay. What's happening with compound growth and decay is they're telling us our percentage yearly, but they're charging us in a different interval than that. So we get a bigger formula. But let's look at the differences first. What the differences are, it's this n. And it's in the exponent and it's dividing the rate. What they're doing is they're taking our rate and they're taking our yearly rate and they're dividing it into smaller portions and then charging us more often. Because what it allows to do, if we think of this as debt, is it allows them to charge us more money because it builds the principal faster. And there's an assignment that you'll work on that you'll see that. Now, T still stands for time. It's going to be in years. Your initial is still what you start with. Your rate is still your percentage in decimal form. What changes here is we have this value of n. And n is the number of compounding periods per year. This is where the wording can get tricky, okay? So what you have to do when you figure out this value of n to set up this formula, you're going to be given words like what I have down here on the bottom. And you've got to figure out how many of those items are in each year. So the first one is yearly. How many years are in a year? 1. That's the weird one that tends to get people. If it says yearly, you could still use this. That just becomes 1. Quarters, quarterly. How many quarters are in a year? How many quarters are in a dollar? Because what does quarter mean? If you take pizza and you divide it into quarters, you get 4 of them. So what they're saying is quarterly would be 4 times a year. What about monthly? How many months are in the year? That's 12. Weekly, and that one, this is where it starts getting a little bit tougher. Weeks doesn't come out to a perfect number if you try to do the division. For this concept, weekly will always be 52. In all financial terms, there are 52 weeks in a year, even though it's not perfect. Daily, how many days are in a year? That's 365. And then you can see we could keep going further and further down. Hourly. I don't expect anybody to know this one off the top of their head, but how would you find hourly? Well, I know there's 365 days in a year. How many hours are each one of those days? That's 24. We could use that to calculate this one. We won't do a ton with hourly or anything else, but I'm getting the idea that any of these terms we could find. Minutes. Well, I take however many hours there are. I multiply it by 60 because there's 60 minutes in each hour. That would be minutely. Now, there's one over here that I hadn't uncovered yet. Semi-annually. And really, we're talking about this word semi in front. Semi-annually is twice a year. If you ever see the word semi in front of any one of these things, it means that they're charging you twice. They're applying the interest twice for each one of those periods. So semi-monthly, we know monthly is 12 and semi means twice, so that means this one would be 24. It's actually, you got to think the word semi is like multiplying by 2. It can double the compounding periods. And the game here with compound interest, the more often your interest compounds, the more overall principal builds. And if you think of principal, I would talk about this one with a lot of debt because it makes a little bit more sense. If you think about it like credit card debt, the more often they charge you interest on that, the more money you owe them, therefore the more money they make. One more to go. So when we talked about this compound interest, what happens as you work your way down this is you find out after you do hourly, minutely, stuff like that, that it stops mattering as much because you're not seeing that big of a difference in this compound. And what you end up seeing is there's a limit to how often you can compound something and actually see change. And they call that continuous. Now, continuous, we deal with continuous. We have a special number. It's kind of like pi. You get initial, this base of E, rate times time. All these other things still stand for what you expected to. Time is still time, rate is still the rate. Initial is what you start with, but this E is different. There's a number that's equated to that. But it's also a button on our calculator for when we go to actually calculate these things. Because what we found out is that there's a limit to how often you can compound things, and it comes out to being this number E. And you'll see that in Wednesday's assignment as we work through the table and the notes, okay? But when you look at it, it is, let me see if I can find it on Desmos. Because I've never found it on Desmos, so I gotta look. There it is. It's right here. So if I have to delete all this stuff, E, and if I put in 1, it tells me that number. That number E is actually 2.718281828. It continues on forever, kind of like pi does. And you don't need to memorize it other than if I see E, I need to find that button in the calculator so I can do that calculation, okay? But it's in here in our function menu. Now, key things to look for if you're going to end up having to do this continuously compounded. The problem is going to say the word continuously about 99% of the time. If you're supposed to use continuously compounded growth or decay, you should see the word increasing continuously, continuous decrease, something like that. You should see the word continuous in there somewhere, okay? So when we talk about these first examples that we're going to work through, let's identify which one of our growths this is. So number 1 says, how much will your $25,000 car be worth in 3 years if it depreciates at 6.7% each year? So we have an initial, we've got some time, we've got a rate, but which type of growth is this? Is this continuous? Doesn't say continuous, right? So we know it's not continuous. So that means we're down between compound and this regular idea. So the key thing with compound, it should say the word compounded in it, because it's got to tell you that interest is compounded by one of these terms, yearly, quarterly, so on and so forth. So since this one doesn't say continuous or compound, this is this regular. So our balance is our initial, 25,000. Now, this car depreciates, right? Cars most likely don't usually gain value, they lose value. What does it mean to depreciate? Does the value get more or less? It gets less. So when you do that, what you have to be careful with is that this percentage is actually negative. So this is negative 0.067. And we're going to take that to the power of 3 to find that balance. So that's 25,000. And we need to do this subtraction. So that's 1 minus 0.0967. So let's go back and actually do that. 1 minus 0.067. I'm sorry, that's not what I meant to do. 0.933. So our base is actually 0.933. We're going to take that to the third. And that'll tell us how much our car is worth in 3 years. So let's actually calculate that. It's 25,000, 0.933. And we're going to go to the power of 3. We end up with $20,304.16. Not bad for a 3-year-old car. All right, 2 and 3. So let's just identify, and then we'll go back and we'll actually work the problem. You have credit card debt of $8,500 with an APR. Now I'm putting this in here so that we understand what this word means. APR is annual percentage rate, which means yearly, of 18.95%, and this is compounded monthly. So because it's compounded monthly, this is compound interest. So compound growth decay. So that's going to be our bigger formula, which is our initial 1 plus R over N T times N. And we'll go and we'll plug in numbers and we'll find that answer before, because identifying in the beginning is probably the tougher spot. Colony of rabbits has a continuous growth rate. So that means this is continuous. This is the one that's actually on this slide. So continuous is our balance that we're looking for. Now notice I still kept the word balance even though we're counting rabbits this time versus money, because it just means a population. You can count anything and call it the balance. So it's going to be our initial E rate times time. So let's go back and plug this one in and find our answer. So our initial here is $8,500, and we're 1 plus the rate. Now our rate's 18.95%. We need to make that a decimal, so we move it 2 to the left. Our time is 3. But what we need to figure out is we need to figure out what compounded monthly means. Compounded monthly tells me that the number in the exponent and in the denominator of this fraction should be 12. Because there's 12 months. in each of those. I'm going to run out of space, but we'll plug that in and we'll find the answer. So let's actually go and do it right now. So we had 8,500, 1 plus 0.1895 divided by 12. The power of, was it 3? Yep, 3 times 12. To the power of 3 times 12. And notice what just happened on the screen. I don't want that 12 to multiply. I want that 12 to be in the exponent. You got to be really careful to make sure it matches up to everything that you had. And it's really not going to want me to do it. So we're going to put it here. Because it doesn't matter what order I multiply it in. But I see now that my answer is 14,000. $941.22. Talk a lot about credit cards in this one because credit cards are one that can get yourself in trouble, but you look at that growth, that's almost doubled in 3 years at 18%. So it's one that you want to pay attention to because that type of growth is dangerous. And after 3 years, it continues to get more and more. Last one, continuous. So we're going to go, our balance is going to be our initial, which is 20. E to the power of our rate. Now remember, put it in decimal form and it's positive. 0.25. And how many years? I've got it covered up. 7 years. You're going to multiply that by 7. So this up here needs to happen in the exponent. And again, this is one we're just going to need to go through and calculate at this point. So we had 20. And now you're going to use the function key here. And it was 0.025 times, and there it is, doing it again. So let's see, in Desmos, I think if you put that in parentheses, it's going to be a good idea. Was it 3 again? 7. Make sure what you see on your Desmos screen, if you're using Desmos for this, which I think it'd be a really good idea too, because it's a whole lot better than trying to do it on your handheld calculator, because you can actually see it the way it's supposed to be written. We get 23.82. So this tells us that our balance is 23.82. Now, quick thing about how to write your answers for this. The first two were money, so I rounded up the 2 places because we typically count money in pennies, right? Should I leave rabbits at 23.82? Why not? What's 0.82 of a rabbit? Yeah, we're not going to go there. Either have a rabbit or you don't have a rabbit. So with this one, you run around to a whole number, and it's usually round it like you normally would. If that's 0.5 or more, round it up. So we would say that this would be 24 rabbits. The key with this whole beginning part is about calculation and reviewing how this works. Identify which growth you have so you know where the numbers go in the formula. Use the Desmos scientific calculator. It'll make life immensely easier for you, okay?